So we're going to break our collisions down to essentially two types. There's an inelastic collision, which is a collision where you do not conserve mechanical energy. The perfectly elastic collision is a collision where you do conserve mechanical energy. And typically a collision like this would be something between two very hard objects, such as two billiard balls or two steel balls. That comes very close to being perfectly elastic. So again, our two kinds are elastic, and essentially we can think about this as being the kinetic energy is conserved in an elastic collision. In an inelastic collision, the kinetic energy is not conserved. And so one thing is we want to be real careful how we know which is which. And basically, for an elastic collision, you usually have to be told that it's elastic. You could be, given a problem where it says something like two perfect billiard balls collide, then you can kind of read into that. Inelastic collision is generally everything else. So if you're not told it's elastic, you can usually assume it's inelastic, or either that or you just don't know and you have to actually figure it out yourself. Now, one thing you got to remember is that during a collision, momentum is almost always conserved. So you don't want to get so worried about the kinetic energy that you forget that the momentum is almost always conserved. Let's look at an example, a classic example of an inelastic collision. So we have two boxes. Box 1 with a mass of 20 kilograms is moving with a speed of 5 meters per second towards box 2, which is initially at rest. When they collide, they stick together. We want to go through and figure out what their speed will be right after the collision. So here's our setup, the initial and the final, and so we can conserve momentum. It is a collision, and so we know that basically the collision forces are much bigger than anything else acting. I think I even said in the problem it was frictionless. So we can conserve linear momentum in the x direction. And so we set this up. Here we got the initial momentum of box 1 is 20 times 5. The initial momentum of box 2 is 50 times 0. And afterwards, we can combine their masses and treat them as one object since we know they stick together. And if I do this, I can go through here and solve for the final speed as being 1.43 meters per second. And now we can take this and investigate this problem a little bit. So first of all, I can look at the two momentums. Here's the initial momentum of the one guy that was moving, and afterwards here's the momentum of them together. This is essentially the same if you just aside from some rounding errors. And so what's nice is you can always prove this to yourself afterwards. Okay, you can always go back and show the momentum is really equal, which is nice to make sure you didn't goof on something. Now, if you look at this example, the kinetic energy is not conserved. The kinetic energy of our equation is 1/2 mv squared. So initially, the only block moving is this guy, 20 and a speed of 5. Afterwards, they're moving together 70 and 1.43. So the energy goes from 250 to a little bit less than 72. And so energy is not conserved. So energy is lost here during the collision. It's lost in heat, sound, and in deformation when the objects stick together. So there's a couple of different places where the energy can go. But the key is whenever two things stick together, there's always going to be some kind of deformation, and so you're always going to lose some of your kinetic energy. So that's a key. That can be one of the hidden tricks that we can do on a question, is to say if something sticks together. In that case, you know it has to be inelastic. Now with elastic, say we have a collision between two objects. Now if you have two objects colliding, we know we can conserve the momentum. So here's our initial side, here's our final side. We can conserve momentum like we've been doing in class in the last couple times. Now in elastic collision, you have another equation where you conserve in a similar manner the kinetic energy. And so again, you have the initial side over here and the final side over here. So what's nice is you have two equations. And so if you start with, say, any two velocities, the two initial velocities, you got two equations you can solve for the two final velocities. So this system is, you can actually solve for the two final velocities. You don't have to have any information about the final velocities if this is in fact elastic. Now one problem is these two equations are kind of nasty. So one trick that we do is if you combine equation 1 and 2, you can get this equation here, which essentially sums up the same information that's in equation 2. And this says that the speed of approach equals the speed of recession. All right, you look here, this is the relative velocity of the two objects finally. This is the relative velocity initially. Now this equation here can be used in conjunction with equation 1 to solve essentially any 1D elastic equation. Let's see, or elastic collision. Let's see how this works. So here's a standard elastic collision. So you're told in the problem it's perfectly elastic. Remember, you usually have to be told that. And so here we got the mass of 200 kilograms and a velocity of positive 2 meters per second. Let's just assume that we're calling this to be our positive x direction in the picture here. And over here, we've got this guy with a mass of 100 grams moving in the negative 3 meters per second direction. And so let's go through and find the two final velocities of these balls. So the first thing is we have momentum conservation. So I can set this up. Here's the initial information for the two balls that were given in the last problem. Remember that this is a -3. I can go through and do some math there and get my final equation looking something kind of like this. So now with a new piece is this relative velocities. We don't know anything about the final velocities, but we know everything there is to know about the initial velocities. So V2 initial is -3, V1 initial is 2. Remember, this negative sign is part of the equation, so be careful. It's really easy to flip one of these around and get an incorrect answer. And so if I figure this out here, so it's -3, -2 is -5 times a negative. I got a +5, and then I just swung this initial guy outside. And so here we have two equations, two unknowns. I know what these masses are. The only thing I don't know is the velocities. So this is just algebra now. The physics is over. So maybe stop and pause here and see if you can work through these two equations, two unknowns. All right, so here's the two equations. So I'm going to basically plug this equation into the other one. So I'm plugging in V2 final into where the V2 final was over here. So my first step, I'm just going to plug in the masses. My second step, I'm going to distribute this 0.1 times the 5 and the V1 final. And so when I do that, I get one term that has a V1 final, one term that's just a number. So this guy I can bring over here, and then I'll combine these two guys here. And I get 0.3 times velocity 1 final equals this number here, and I'm ready to solve for my velocity 1 final. Now what I can do is take this and basically plug it into this equation over here. So once I know V1 final, I can solve for V2 final. So we get these two numbers here. Now this is just algebra, however it's not very pleasant. Knight has a different approach. You can check out his approach. This is one case where I'm a little bit different than him, but both approaches are just fine. But it's not, so it works out here. You can solve for the final velocities.